Determine whether the given flow fields are 1D, 2D, or three-dimensional flow fields. In fluid mechanics, the dimensionality of the flow field depends on the number of spatial variables that define that flow field. Let's move to the item A, which is given as V is equal to 2xi plus yj. We see here that we have x here and we have I over here. So this flow field is a two-dimensional flow field. And it can be seen over here that as we move in the x direction, the arrows get larger. Also, as we move in the y direction, the arrows change as well. So this is a 2D flow field. Now let's move to item B, which is given as 2xi plus xj. Now, you might be tempted here to say that, okay, we have the I component, which is the component of x, and the j component, which is the component of y, and say that this is a two-dimensional flow field as well. However, as it is mentioned, the number of spatial variables is what we care in fluid mechanics to determine the dimensionality of the flow field. Here, we only have x as the spatial variable. So this is actually a one-dimensional flow field. We can see it here that as we move in the x direction, the arrows change. They get a larger y component compared to lower x values, and they also get bigger, which is because they also get a larger x component, I component. However, you should notice that if we take a constant x, let's say 1.25, and observe as we change y, what happens? We see that the arrows are actually constant. For example, here. So this means that this flow field does not depend on y. So, as mentioned, this is a one-dimensional flow field. Now, let's move to item C. In item C, we have x in our variables, we have y, we also have z. So this is a three-dimensional flow field. However, you might notice that we only have an I component and a j component, but not a k component in our output. As mentioned before, this should not confuse us to stating that this is a 2D flow field, because our flow field is also changing with the z and two other spatial variables, which are y and x. We can see the flow field in the plot here, and we can even take a two-dimensional cut of this flow field and basically project the arrows associated with that cut onto that plane, and it would look like this for the value of x being 1 over here. Let's see, if x is 1, we are actually talking about a plane like this. In this plane, since we have fixed the x value, we have a y z plane, And we can see that as y changes, the arrows change. And also as z changes, the arrows change as well. Hence, this also shows that this is not a two-dimensional flow field because it changes with all the three spatial variables. Now, item D is actually a special item because here, even though we have an I component as the output, its coefficient is a constant number, which is 2. And we don't have any of the spatial variables x, y, or z. Hence, we would say we have a uniform flow that has one non-zero component. And we can also show it in a three-dimensional space, but this is still just a uniform flow. We wouldn't be able to say this is one-dimensional flow even, because it doesn't even have one spatial variable.